So this is the final lecture in the productivity track, and before I forget, I want to tell you that Jared, Jim and I, all of us are going to be around after, so we don't have a formal hands-on today, but we will be around for as long as people want to engage with us, and if you want to work on your specific problems with us or just come ask us questions, consultation or whatever, we will be there, okay? So, and if you don't want to do any of that, we give you a free evening. How's that? Okay. So this lecture is about software refactoring and documentation. So the things that I want to make you aware of right off the bat is that this lecture is not about how to do refactoring for your specific problem. It doesn't tell you about tools because, to be very honest, there aren't that many tools that will help you with your refactoring process. And it is not any sort of detailed methodology either, and that's because refactoring is a very, very project, it's usually very specific to individual projects. And so you really have to devise your plan, your methodology for your project, keeping its own constraints in mind. What this lecture is a methodology for how to plan your refactoring plan. Okay, so it's a plan for a plan kind of methodology. And what I will tell you is basically point out possible pitfalls and workarounds that you will have, and also examples. So Flash, we keep coming back to Flash or Trillinos because that's the software that we are representatives of. So these are the ones we understand the most. That's not to say that these things don't apply elsewhere, but I mean, these are the specific examples we're picking up. And so Flash has undergone three major version revisions until now, and is undergoing a fourth one. And so I'll give you examples from where we found the pitfalls, things that we had to do, how we did the planning, etc., as an example. Okay. So, So there is a general definition of refactoring, and that is in the context of object-oriented programming, and the refactoring is where you change the way your code is written without necessarily changing the functionality. We in the scientific world, or at least we in the Flash world, stretch that definition a little bit in that we don't say that our refactoring is going to keep having that particular section of code perform the exact same thing. When we are talking about refactoring, we are talking about actually things like deep architectural changes to the code framework. So, but the basic capabilities and features that the code provides to you still remain the same at the end of the refactoring. So it's a much broader interpretation. And the reason why we do this is because within the context of HPC software, the degree of change is motivated by many, many factors, and so the redesign may be needed at a higher level. So before you start out on the process of refactoring, it is very important to take a few considerations into mind and plan for them. One of them is you should know why you're refactoring. Is it really necessary? Because refactoring is of scientific codes, because many of them have a lot of legacy components and require very, very specific expertise. It is a messy and difficult and complex and error-prone process. And so before you embark on it, you should really convince yourself that you need to do this. And even before you start your first step in refactoring, you should know the limit of change that you want to see in your code. So where you want the final code to be, because it's very easy to, as you start to do refactoring, you start to look at code. And this I'm telling you from personal experiences, you see, oh, this is also very, very yucky. Why can we not change this as well? And so clean up the code here also. And before you know it, you've gone so deep down into the rabbit hole that you will never succeed in getting anywhere beyond that particular section of the code that you were looking at. So it's very important to know where you want to go. How deep a change do you want? How much code do you expect to be affected? Upfront, estimate the cost, And the cost is not just in terms of the amount of developer time that it's going to take. The cost should also be taking into account the disruption that might happen to the production schedule, because usually when you're doing a refactoring of the code, chances are that someone is using that code to do their science runs, and there is likely to be some disruption within their schedule when you're doing these changes. And before you start to do the refactoring, it is important to get a buy-in from the stakeholders. And this will become, that's because that includes just the end users who are not necessarily part of the development, because in one of the version changes in Flash, it so happened that architectural changes happened from Flash version 1 to Flash version 2. There was some conflict or some misunderstanding between the developers and the users of the code, the scientists in the center. For about 2 years, they never switched over to the new version of the code. They just kept adding stuff to the old version of the code, and the whole thing became a nightmare for the code developers. So it's very important to get their buy-in, because there's the added advantage that if you get buy-in from the stakeholders, from the users, it's an incredible resource in developing your testing regime while you're doing the transition, because they have the intuition, they can help you design good tests. That's part of the benefit. So there are many reasons one can be doing refactoring. It can be because you just want to have a better architected code, that you want to, for example, the first version of change in Flash was just to get rid of the common blocks and to get an inventory of the data that was being used in the code and so on. The biggest one why this has become such a hot topic is because of the platform heterogeneity. It is that almost all codes that are out there need to do some form of refactoring in order to be able to exploit these machines, whether it is at the level of having target-specific implementations or having deep architectural changes. They all have to do it because they have to deal with these platforms. So once before, this kind of paradigm shift had happened, and this was when we had moved over from vector machines to distributed memory parallel machines. In vector machines, the memory was flat. You had memory banks, and so your different data items came from different banks, but you didn't have the memory hierarchy, so data locality didn't matter. In fact, the larger vectors were the more suitable ones. When we switched over to RISC machines, then all of a sudden there was memory hierarchy and data locality became important, and that's why major deep architectural changes happened. And it's a similar reason right now. And the driving reasons for these transitions is always performance, because you could still run a vector code on a RISC machine. It would still give you right answers. It would just take a very long time to do it. Similarly, all of the distributed memory codes that we have right now will run on these heterogeneous platforms. It is just that they're going to take a very long time to run, much longer than they do on the current crop of machines. Okay, this one I'm going to skip. And there are more slides in this presentation than I'm going to talk about, because they just have information. And instead of me reading them out to you, you can read them for yourself later. What I will spend time doing is on slides where there is some explanation, some useful information that is to be conveyed over and above what's written in the slide. Okay, so this one also I think I will skip over. All right, cost estimation. This one is a very important consideration to have, because it is something that people mostly underestimate. And if you have a really large complex code, the process of doing the cost estimation itself can be very costly, and that's why most projects do a pretty terrible job of cost estimation. So there can be many reasons for it. Insufficient understanding of the code, insufficient provisioning for verification and obstacles, refactoring, etc. It overruns time and budget, etc. So again, emphasis is know the scope, sticking to it, plan for all stages with contingency factors built in, make provision. Also assume that the tests that you have in existence are not going to be enough, that more tests will need to be developed during the process of refactoring and therefore make provision for it. Because remember that we go back to the original point that if you don't have sufficient number of tests available and you start on the process of refactoring, you are bound to incur technical debt. So the cost estimation, another part of it is that has to be worked in is that if there is a coexistence of production and development, then there is always a potential for branch divergence, which means that reconciling the branch divergence is a part of the cost involved. And this can be done through policies for code modification in the sense that, and this actually I'll go into it much more detail with the example, but also, so the first part of the planning is the on-ramp plan. So this is the on-ramp plan has to be proportionate to scope. So if you are, for example, working in a situation where, say, this is your whole code and you are just changing small little parts of it that are sort of scattered and not very intertwined, it is possible that if you were to do it all at once that it won't be such a bad idea. But if you are in a situation where your code is going to start out looking like this and it's going to look like that, doing all at once is a really terrible idea. That you really need an on-ramp plan. And so on-ramp plan can be done in one of two ways. If you're working with the deep code architecture, for example, one way to do it is sorry, it hasn't, right. So one way to do it is incrementally, if at all possible, which means that you take one section of the code away from one section of the code out, you modify it, test it, bring it back into the original code. And similarly, you can do this, apply the same process to all of the sections under the code and you finally have a code, or else you build a new infrastructure completely separately, test this infrastructure, verify its robustness, and then you start to move the code sections into the new infrastructure one at a time. In case of Flash, we have followed this second methodology a lot more than the first methodology. So verification, right. Verification is an absolutely critical component of refactoring. So it is important to understand the needs that you may have during the process of transition, which means that you should really know the map from here to there. And you should know your error bounds. Just like in testing in parallel environment, knowing error bounds ahead of time for all tests, even the simplest tests that you were counting on to do bitwise comparability is not going to exist once you've done the refactoring, because any change in order of operation changes the floating point calculations, and so you really do have to know your error bounds. You should check for coverage provided by existing tests and develop new tests. Make sure the tests exist at different granularities, and this should be definitely at integration and system level tests. Now, experience with Flash. So Flash has these class of components or units that exist within it. So there are these infrastructure units, which is the grid, managing the discretized mesh and the Lagrangian framework, the runtime parameters, the I/O, and then there are physics capabilities such as hydrodynamics, MHD, gravity, burn. There are the profiling units which monitor the progress of the simulation, and then there are these two specialized kind of units. Driver is the unit that sort of orchestrates the interaction among different units. In addition to that, it implements the time stepping algorithm. Okay. Simulation unit is where an application within Flash actually starts. So this is where you define your initial conditions, you define the components that you want to include. If you want any customization, then you put an implementation or, so the way Flash's configuration works is that you can pick up any source routine from anywhere in the code, and you put its customized version in your simulation unit, it overrides the code existing elsewhere. So this is a very elegant mechanism that is for customization, which is completely non-intrusive to the main code base. So that's what this unit does. Now, I'm not going to dwell on all the various version changes, and I'm going to skip over these slides. You can read those slides later. But the thing that basically happened between the change from version 1 to version 2 versus version 2 to version 3 was this lesson learned during version 1 to version 2, that because the stakeholders were not brought into the picture, the change that occurred was not adapted by the users of the code, and that it took nearly 2 years for the code to be adapted by the center scientists. What that exercise was, Flash came into existence as a sort of bashing together of 3 codes that came from 3 completely different groups. And so the version transition from 1 to 2 was basically a matter of doing some, imposing some amount of data discipline onto the code. So all of the data was yanked out from every unit that was in the code and put into a central database. What that did was it inventoried the data, and you got the common blocks got eliminated, and you got some sort of an idea of which units were handling what kind of data. But this wasn't a complete change in the architecture, which the modularity hadn't been obtained, because what still remained true was that every unit then needed to query the database, obtain the data from the database, and so there was no arbitration on who owned data or who could modify it. And so the things that were not working out with this particular transition were that the on-ramp time for anybody coming into the group, it took nearly 5 to 6 months before they understood the code or could start to contribute to the code. And it was very easy for people to make mistakes whereby what the code that they were writing would modify data that they weren't supposed to modify. And so it was, another round of modification was needed, and here the database was decentralized, and the data scoping was defined in much more clearly. The code units became encapsulated, the testing regime was started, and so on. So this is the current version of the current architecture version of the code that is in production, and that version is Flash 4. The 3 to 4 version was basically just capability addition, not much of an architectural change. The one that I want to dwell on now is the version change that we are undergoing now, and that is version change from Flash 4 to Flash 5. So, and I'm not talking about all of this transition also, because we are doing this refactoring also in stages, and this is where I reiterate the fact that in each stage we know exactly how much of change do we want to have happen, and no more and no less than that. So in this instance, I'm talking about the change where we have the AMR supported by Paramesh, which has been around since 1994-5 and has not been in active support for a good 15 years now. And so as we face platform heterogeneity, Paramesh as is not an option for AMR support into Flash. And so we decided to add AMRX as an alternative AMR capability within Flash. So this was the idea of the whole premise of this particular refactoring that's going on. And so the plan is that Paramesh and AMRX should coexist, which means that this interface here, the grid main, the API of this code needs to be adapted in such a way, or its implementation needs to be adapted in such a way that it can switch between Paramesh and AMRX as needed. So that was the first level of interaction of change we needed. And the second one was that all of the physics units now, because AMRX works with smart iterators, all of the physics units now need to interact with grid unit differently. Okay, and so this is what the changes look like, is that at this level is where the all of the change needs to happen. So the grid unit implementation needs to work with the old with whatever physics capabilities exist from the whole code. So the refactoring plan is There's the design phase where we figure out the degree and scope of the change and we formulate initial requirements. Then we run prototyping and then we do the implementation to recover from prototyping and expand and implement design decisions. And I will come back to this figure later on to outline the specific process, steps in the changes in the refactoring phases that happened. So the first phase was design, where we sat down, we argued, we made pictures, we took figures of the pictures. Sometimes the arguments got heated because we didn't immediately agree on the degree of changes we needed, etc., etc. In the process, we understood the definitions and abstractions. We understood what things we could keep from paramesh as is, what things needed to be changed for AMRX. We understood what physics units demanded from the grid unit, and we designed the data structures and interface update that needed to happen. So this was basically minimal prototyping with no verification, this whole design phase. Second phase was prototyping, where we did the implementation with quick, dirty, and light. And this was done with this absolute understanding that none of this is going to make into the production code. This prototyping was just for the purposes of design space exploration. And so we implemented new data structures, evolved and iterated between paramesh and AMRX, explored the physics and grid unit interface. What we did was we created a very simplified version of hydrodynamics, which didn't even do things like flux correction, etc., the simplest possible implementation that we could have, and started to test the infrastructure with that, so that we would discover the use patterns, etc., and then we would adjust requirements and interfaces. So here we did quantitative regression testing with paramesh, and then proof of concept with AMRX via qualitative comparison with paramesh, because the answers were not going to be exactly similar. The third phase was implementation, where we actually cleaned up the code, implemented testing, started the testing regime, and so on. And so basically here the code started to get cleaned up and the documentation started to get put into the code, and we started to use one of the actual physics units. So what we did was we made simple hydro work with both paramesh and AMRX before we actually started to deal with the whole big hydro thing. And so we got the AMRX, and actually let me go to the figure again to explain this. So the steps are outlined here. So first part is requirements gathering, and that was basically working with simple hydro and solidifying our interfaces, data structures, and iterators. Then we modified the grid API and had that as a new alternative implementation, and then built iterators over paramesh so that the behavior of physics units interacting with paramesh would mimic how the behavior was going to be with AMRX. So notice that all of these changes are happening small, step by step, incrementally. The next step was make sure that the hydro driver is consistent between AMRX and paramesh, and that we actually have other AMR functionalities such as flux correction and top level interaction. And the way in which we made this happen was we had paramesh and AMRX working side by side, where paramesh would create the grid. We would extract metadata from paramesh created grid, feed it to AMRX, so that AMRX would think that this was the metadata, that it had generated the mesh, and then we would do the physics units with AMRX iterators so that they think that they are getting the data from AMRX. So in this way, what we were able to do is we were able to enforce that the grid produced by AMRX and the grid produced by paramesh were identical, and they could be, and that we could do a comparison between the data produced in these two ways. So this was the incremental way in which we planned and made this whole transition happen. So now Flash 5 is in public release. It's available on GitHub. It will not do all of the production simulations of Flash, but if you were looking at simple simulations that mostly just need hydrodynamics and a few other capabilities, you can actually exercise that right away. Any questions on refactor? Because now I move on to documentation in the last 4 minutes. Okay, documentation. So the life cycle of a scientific software looks like this, that you have the initial development where you're doing a requirement analysis, design, implementation, verification and validation, and these arrows indicate that these things just have short circuits all over the place because of the nature of the development that we have. And then, but once you have a slightly stable code, then you have a maintenance and ongoing testing, release, distribution, user support, and then you can have integration of a new resource or capability addition that also goes into requirement analysis and this whole cycle. So documentation needs are different in these different phases. The first part, initial development, is where we do the requirement analysis, which means that we look at what are the expectations from the software, what kind of capabilities do we want to have in the software, the minimal number of them, the solvers that might be needed, the constraints that the software is going to be put up with, and how will all of these capabilities and the infrastructure, etc., is going to be tested. So in Flash, for example, the very first version, what was known right away was that the same code was going to be used for different regimes and different functionality, which means that we wanted some sort of a composability and configurability in the code, that we needed shock hydrodynamics, we needed equation of state for degenerate matter, and we needed adaptive mesh refinement, and that we needed a battery of tests. So this was the requirement gathering part of the original version of Flash. The second phase is the design phase, where you look at the overview of the software, you design, you specify what the architecture of the code is going to be like, what are the interfaces going to be like, the coding principles and coding standards. Coding principles and coding standards are two different things. Principles refer to the practices that you will follow, whether you're going to have an object-oriented code and how much of object-oriented code, etc. Whereas coding standards can be things like naming conventions of functions, naming conventions of variables, and so on and so forth. Documenting them explicitly is very useful because when you have new people coming in or people wanting to contribute to the code, you can point them to these documents instead of having to answer these questions over and over again. And so in Flash's case, there are design docs which were basically snapshots of discussion. So we'd be whiteboarding. At the end of a session, we'd take a picture of that whiteboard and we would put it in and they actually exist in the SVN repository of the earliest versions of Flash, these design docs, so we can always go back, which, so we have information about how we went through the design process without actually having to write them, and they're still extremely useful. So no one took extra time, but we have the history of it, right? And there is an online example of a unit, step by step, what a unit architecture looks like, and then there are coding standards which are documented. Then comes the implementation. And so in implementation, you write things like headers in terms of what is the functionality of a particular function that that this function is, the inputs and outputs, the outcomes, the API, which means the tool, interfaces through which a unit is or that function is interacting with other parts of the code. And usually you can do that with some sort of an auto-generative documentation, whether that is Doxygen or, these are all various examples of it. A very important part of the implementation is this inline documentation, and this inline documentation is not just information about the arguments, the variables, etc., etc. A more critical part of this inline documentation, which has been invaluable for us, is if you made a particular design choice in writing the code in a specific way, why did you do so? It goes back to some of the things that Jim also mentioned, or about the fact of there being really bad code and why there was bad code or not. If there is documentation accompanying that bad code, you know why it is this way and how much liberty can you take with that code in terms of refactoring it in future. And then you come to the point where you're ready to release the code and it's about to go into maintenance mode and release and distribution mode. And at that time, all of this kind of documentation comes into play: user's guide, developer's guide, reference manual, API, and online reference. And that becomes an ongoing process, is that whenever you have integration of new research or capability addition, you have to update the API, you have to update the user's guide and all of this reference material. So on. And so with that, the takeaways from this last lecture are that in order to have good outcome from refactoring, you must know why, you must have already decided how much ahead of time, and you should have a good idea of the cost of refactoring. You should plan and have in your mind worked out a strong testing and verification regime. Get a buy-in from your stakeholders. About documentation, different stages of software need different documentation. And the most important takeaway is documenting of why is as important as documentation of how in your code. And with that, I'm done. Questions? Questions? Yes?
So in the documentation, how long did you spend on each phase? How much time did you spend?
So like I said, the design docs, actually there was no extra time spent because we just kept taking snapshots and kept storing them, right? The inline documentation, it's impossible to keep track of it because you do it as you're writing. Usually the user's guide, etc., they did take a while. And so in the past, when we were releasing Flash through SVN, we usually would set aside 15 days for doing the testing, updating of documentation, so basically feature freezing. We would set it aside, and I would say roughly 20% of that time would go into documentation update. Yeah. Any other question?